Hi there, in this video today we're going to be looking at graphs of logarithm functions. So having a look at the syllabus here, there's only a few very distinct kinds of graphs that we need to know. I'm going to look at a little bit further, which will kind of help enhance our understanding of basic translations of graphs. But the syllabus here, if you look in 4.1.6, says identify the qualitative features of the graph of y equals log base a x, so the basic graph of what that looks like. A is greater than 1, including asymptotes. So we need to know that word there. Asymptote is just a line that the graph gets closer and closer to but never touches. That's what an asymptote is. And of its translations, y equals log base a x plus b and log base a x minus c. So it only mentions a few specific graphs there, so let's get into having a look at what they look like. So I'm going to start here with looking at the graphs of exponential functions, and there's a really good reason for this, is that the graph of a logarithm function is just the inverse of an exponential function. So there's a really clear geometric relationship between these two graphs. So we can draw 2 to the power of x and we know the shape of that thing there, or 3 to the power of x or 4 to the power of x, and what those look like. Just remember what happens if we have something like a half to the power of x, then there's a flip in the y-axis there, so you can see the graph of y equals half to the power of x. We have 10 to the power of x, it would be even steeper. So these kinds of things apply when we start looking at logarithm functions. Okay, so here we've got the graph of y equals 2 to the power of x, you can see in purple, and the graph of log base 2x. So this is to a base of 2. So you can see the shape of the graph is a reflection in the line y equals x, because this is the inverse function. So a few things to note about the red logarithm graph. I'll just get rid of the purple one for now. So we're just looking at that one. So log base 2 to the x here is, of course, log base 2 of 0 is undefined. 2 to the power of something is 0. There's no such number. So one of the asymptotes here is the y-axis. So the graph gets closer and closer to, but it never actually touches the y-axis as it goes down. You see that the graph is going through 1, 0. So a log base 2 of 1 is 0. So we know 2 to the power of 0 is 1. And that's the same with all these basic logarithm graphs. You'll know that they'll be going through 1 on the x-axis. And then you can see at 2 it's at 1, so log base 2 of 2 is 1, so there's that point there at 2, 1. Log base 2 of 4 is 2. Log base 2 of 8, if we scroll across, will be 3. And so log base 2 of 16 will be 4, etc., etc. So you've got the graph going off like that. So there is no asymptote, horizontal asymptote. This thing keeps getting bigger and bigger and bigger, but just at a really slow rate there, okay? So there's a graph of log base 2x. Now if we change the base to base 3, or base 4, or base 5, you can see it's just getting shallower. If we look at the graph there, this is base 5, so it's getting shallower there, but it still retains the same kind of idea, still going through 1 on the x-axis there. So I'll just change this. So here's log base 10 of x, so our common logarithm there. So the shape is essentially the same when we change the base. Okay, so what happens if the base of the logarithm is not a positive whole number if it's a fraction, so if it's between 0 and 1? So having log base 0 doesn't make sense. So we're looking at logarithms where the base is between 0 and 1 now. So what happens to the graph? So here we've got the graph of log base 2 of x, and I can increase that. So there's log base 3, log base 4. Now what happens if we go into the fractions between 0 and 1? Well, first of all, let's look at the basic graph of the exponential function when that happens. Okay, so here's 2 to the x, 3 to the x, here's 4 to the power of x. And you see what happens when we get 1.41 to the power of x. That's pretty boring. That's just line y equals 1. And see now we swap around. So there's a reflection in the y-axis there. So here is y equals a half to the power of x. If I get smaller and smaller there, there's y equals 0.2 to the power of x, 0.3, 0.4, 0.5, 0.6, 0.7. You can see actually if I just scroll this across, it's actually a nice kind of progression between the two. Okay. All right. So let's look at now what that looks like for logarithmic graphs. So here it is here. Here's 2 to the x, 1.3, 1.2, 1.1, 1 to the power of x, which is boring. And here we go on the other side. So there is log base a half to the power of x. So you can see we've got that flip, that same thing going on there as we had for the exponential graphs. Okay. So there's a half to the power of x. There's 2 to the power of x over there like that. Okay, 0.7, 0.6, 0.5, 0.4, 0.3, 0.2, 0.1. Let's just talk about the asymptotes there. The y-axis is still an asymptote. And that's it, just the y-axis. This graph keeps going down off to infinity, negative infinity on the y-axis. But yeah, so the y-axis is still an asymptote. So let's just compare that with the exponential graph, and you can see the relationship there. These two are still a reflection in the line y equals x. Okay, there we go for bigger values of the base. So here's 3 to the power of x and log base 3x, and getting bigger. And then as we go closer there, there's 1.4, so there's some crossover there. There's 0.7 to the power of x, or log base 0.7, and there it is, log base 0.5x in red there. Okay. So let's look what happens now if we add a number on the end there. So we've got log base 2 of x plus a number. So here we've got the graph over here of log base 2x. Here's log base 2x plus 1, log base 2x plus 2, log base 2x plus 3. So you can see basically everything is just moved up that number of places. So instead of the graph here going through 1, 0 on the x-axis, it's now going through 1, 3. So everything's been shifted up 3 places. So this is the graph of log base 2x plus 3. So if I move that right up to 5, you can see now everything has been moved up 5. The y-axis is still an asymptote, but all the points have been moved up 5. Similarly, I could go the other way and say log base ax minus 2, for example. So now instead of going through 1, 0, it's going through at 1 minus 2. Okay, and so there 4, 0 is also on the graph there rather than 4, 2. So everything's been moved down 2. So that's the first translation that you should be familiar with. The second kind of translation you need to know is this one here, log base 2, or log base a anything, x minus c. So let's look what happens when I change the value of c. So here's log base 2 x minus 1. You can see what's going on as I move this is the graph is moving horizontally back and forward. So let's have a look. This is log base 2 x minus 3. So everything has just moved 3 places across to the right. So instead of going through 1, 0, the graph is now going through 4, 0. Additionally, the asymptote for this graph now is no longer the y-axis. It's been moved across 3. So it is the line x equals 3 is an asymptote for the graph. So everything just shifted across 3. So I could also go the other way. So this is let's have a look at this one. This would be log base 2x plus 5. So we've moved everything 5 to the left. So now instead of going through 1, 0, it's going through negative 4, 0. And the vertical asymptote would be x equals negative 5. So here's some basic examples. Drawing log base 3 of x. So base 3 means that 3 to the power of 0 is equal to 1, so it's going to go through 1, 0 of course, but when you get to x equals 3, log base 3 of 3 is 1. So just putting an extra point on there will really define what log base 3 looks like, as opposed to log base 4, which would be going through 1, 4, 1, etc. So, alright, so let's look at this one. We've got the log graph. Log base ax, find the value of a. Okay, so we see it's going through 1, 0, so I don't think it's being translated up or across. So that's given by the formula there. It's just log base ax. So what is the base of this logarithm? We can just put the points in. So at this point here, 9, 2, the y value is 2, and the x value is 9. So we get this, translate this equation here to an index equation, gives us a squared equals 9. So a, if we were just solving that equation, we'd say plus or minus 3, but as we know, negative bases in logarithms don't work, so we can just say a is equal to 3. So the base here is 3. So lastly, let's sketch this one. Remember, a sketch just means a really rough drawing. Doesn't have to be perfectly accurate, just a very basic sketch. Log base 2x minus 3. Okay, so when I'm sketching this, I'm thinking, okay, what are the basic log graph looks like that, and it'll be going through 1. So this is what I'm thinking when I draw one of these. And then I'm thinking, well, what does the minus 3 do? It shifts everything down 3. So instead of going through this point 1, 0, it'll go through the point 1 minus 3. Okay, so you might want to label that point 1 minus 3. Another point on the graph of log base 2x is when x is equal to 2, we get 1. So at x equals 2, it's going through at 1. Log base 2 of 2 is 1. So the point 2, 1 is on this graph. So if you shift everything down 3, rather than going through 2, 1, it'll be going through 2 minus 2. So down here. So there's another significant point there. And if you want to, you could think about the point 4. Log base 2 of 4 is 2. 2 to the power of 2 is 4. So shifting everything down by 3 means we'll be going through 4 minus 1. Now the other thing you might want to look at is what the x-intercept of this thing is going to be. So where it goes through the x-axis, that's when y is equal to 0. So if we look back at our original equation, this is what we want to find out. Okay, so what is the x-intercept? So if I add 3 to both sides, I get log base 2 of x is equal to 3. And then I say 2 to the power of 3 is equal to x. So x is equal to 8. So the x-intercept of this thing here is 8. And that would be another good thing that you could put on this diagram. So if I just extend it out a little bit. So just a basic sketch, and I'll change colors so we can see it. So it's going through like this, off like that, and it'll be going through here at 8, 0. Okay, and then I'll get rid of my original graph. Sketches you can definitely do in pencil, and then I'll just add in those points there. So this point here is 2 minus 2, and this point here 4 minus 1. There we go. There's a basic sketch of the graph there.